So, what's our topic for today?
Professor, you told me write that down.
Oh, we'll discuss nitrogen. Okay, let's start with the fact that there would be no life on Earth without nitrogen.
Since nitrogen is the basis of all proteins.
Exactly. Over billions of years, evolution has successfully fine-tuned atmospheric nitrogen fixation by the biosphere. And then it step-by-step returned from the biosphere into the atmosphere. Furthermore, nitrogen during all of its biochemical transformations is essential for certain living organisms. Meanwhile, the transformation of the forms of nitrogen is also a complex cycle occurring in nature. The nitrogen cycle involves not only the biosphere and atmosphere, but also the hydrosphere and lithosphere. Living microorganisms play a very important, if not to say the main role, in the nitrogen cycle. Nitrogen transformation includes 6 basic stages. Stage 1 involves biological, atmospheric, and industrial nitrogen fixation. What's interesting is that industrial fixation is 10% higher than the total amount of nitrogen produced by biological and atmospheric fixation. Stage 2. Ammonium turns into plant protein. Stage 3. Plant proteins transform into animal proteins. Stage 4 involves the decomposition of both plant and animal proteins. This is ammonification, which takes place after the death of living biomass. Stage 5 is nitrification. It is the oxidation of ammonia nitrogen to nitrite, followed by the oxidation of nitrite to nitrate. Each oxidation is carried out by different bacteria. And finally, stage 6 is denitrification, where nitrite and nitrate are reduced to molecular nitrogen, which comes back into the atmosphere. Thus, the circle is closed, the cycle is complete. And it becomes apparent to us, Ms. Doolittle, that nitrogen is a good guy in all respects.
It seems so.
Exactly. But one must also admit that nitrogen is guilty of many things.
I also think so, Professor.
Okay, let's talk about that. As my colleagues say, there are no toxic substances, there are toxic concentrations. All nitrogen salts that we know have been in biosphere since its early days. However, scientific and technological progress, along with the exponential growth of the humanity, has led to increase of highly toxic nitrogen salts in waste, surface, and even groundwater. We also have to take into consideration that industrial nitrogen fixation is currently at 10% higher than natural fixation. Thus, inert atmospheric nitrogen is the basis for constantly growing toxic salts. And essence of biological purification is
to extract nitrogen from these salts and bring it back into the atmosphere.
And constructed wetland can achieve this goal quite successfully.
As we know, wastewaters contain 2 forms of nitrogen, protein and ammonium nitrogen. For the transition of nitrogen bound in both of these forms in the atmosphere, conditions are created in the constructed wetland artificially. First, ammonification. Second, nitrification. And third, denitrification. Betsy, would you please explain these terms?
That's easy. All these processes are carried out by microorganisms. Ammonification is an anaerobic or facultative anaerobic process where degeneration of plant and animal protein results in ammonia. Nitrification is a purely aerobic process where ammonium is oxidized to nitrates and further to nitrates. Denitrification is an anaerobic process where nitrates and nitrates transform into gaseous nitrogen.
Right. Now could you imagine a constructed wetland with tiny fountains of water squirting above the surface periodically every day? Here's the question. Which of these processes is stimulated by that kind of method?
answer is that the fountains stimulate the nitrification process.
Can you explain why this happens?
Because the fountains cause aeration above the wetland surface. It means they oxygenate wastewater. Only aerobic bacteria require oxygen.
Definitely. Nitrifying bacteria, as we know, consume oxygen. Moreover, during the first stage of nitrification, nitrites are formed, which are much more toxic than ammonium. The second stage is the formation of nitrates. Nitrates are the least toxic of all nitrogen compounds. Therefore, the wastewater treatment specialist's task is to apply appropriate technologies in order to minimize the amount of ammonium and nitrites at the outlet of a treatment facility. Taking that into account, Betsy, let's consider a hypothetical constructed wetland. The type doesn't matter. Let's take any plant from this constructed wetland and let's have a closer look at the processes occurring near the roots of this plant. By the way, Miss Doolittle, what are these processes?
These are the transformation processes of the various forms of nitrogen, Professor.
Exactly. The essential point to remember is that every plant root develops an aerobic microzone around itself, around which, in turn, an anaerobic zone develops. The development of these two zones results in two basic processes: nitrification and denitrification. These two processes effectively remove nitrogen compounds from wastewaters. Makes sense?
Yes.
Excellent, Betsy. If everything is clear to you, why don't we solve another problem? You're welcome to come out to the board. Please, calculate the amount of nitrogen removed by a wetland in kilograms per day when we know the content of 3 mineral nitrogen forms in the wastewater at the inlet and at the outlet. In addition, we know the average water flow rate of the wetland. Please, write down the input data.
Professor, can I make a data table?
Yes, of course.
Good. The first column represents mineral forms of nitrogen.
Okay.
The second column is nitrogen concentration in wastewater at the inlet in grams per cubic meter. 41.5, 0.5 and 0.5 once again. The third column shows nitrogen concentration in the treated water at the outlet, also in grams per cubic meter. Are you keeping up, Miss Doolittle?
Yes.
Okay, I'll dictate. 2.8 grams per cubic meter, 0.02 grams per cubic meter, and 9.8 grams per cubic meter. Additionally, the water flow rate in the constructed wetland is 100 cubic meters per day. So you have to
Calculate the amount of nitrogen removed by a wetland per day.
Is the problem clear?
Yes, it is. We will use a well-known formula, Rn equals. One moment, Professor Higgins. This is quite simple. I have the answer, sir. 3 kilograms of nitrogen is removed from the wetland per day.
The answer is correct. But I have to say that 3 kilograms of removed nitrogen per day, which makes up 70% of incoming nitrogen in the wastewaters, is not an impressive result. There are constructed wetlands which can remove up to 95% of nitrogen. In this regard, Betsy, it's useful to highlight the factors that influence the intensity of nitrification and denitrification processes.
These factors include water temperature, the amount of substrate for bacteria, acidity of the water, and certainly the concentration of dissolved oxygen.
Well done, Miss Doolittle. I will soon become your student.
You are flattering me, Professor.
Maybe just a little bit. So I have prepared some more questions for you as a wastewater treatment specialist. Let's imagine a constructed wetland, for example, with a horizontal subsurface flow. And let's consider once again both processes taking place in this wetland, nitrification and denitrification. What is the essence of each process?
Nitrification is a biochemical process by which ammonium is first converted into nitrates and then into nitrates. Denitrification is a biochemical process where nitrates and nitrate turn into atmospheric nitrogen.
Exactly. So, Here is the first question. What is the pH shift, acidic or alkaline, of the water environment during these processes in the constructed wetland?
Okay.
And here's the second question. Which type of the pH change, acidic or alkaline, inhibits each of these processes? Take your time, Betsy.
I'm ready to answer both questions.
Go ahead, Miss Doolittle.
The first answer is that nitrification makes pH level shift to acidic. Denitrification makes the pH level shift to alkaline. The second answer is that nitrification is inhibited by the acidification of the environment, and denitrification, in contrast, is inhibited by the alkalinization of environment, if I'm not mistaken, Professor.
You want me to give you a compliment, don't you, Miss Doolittle? However, your answers didn't exhaust the topic of our lesson. For us, as wastewater treatment specialists, it's important not only to characterize biochemical processes taking place in a wetland, but also we have to take into consideration... Betsy, what do we have to take into consideration?
To be honest, I'm not sure.
I'll give you a clue. We have to take into consideration a biomass of bacteria responsible for the important wastewater treatment processes.
Oh yes, I do remember. To improve the water treatment effectiveness, we have to select the bacterial zoonosis, which means we have to grow the biomass of useful bacteria functioning in each of these processes. And for this we should...
Excellent. And what we should do, we will discuss tomorrow.
But maybe today we can outline the key points.
I'm already running late for the editorial board meeting. Please write down the topic of our next lesson on the board. The selection of bacterial zoonosis in constructed wetlands.
Professor, it's raining outside. You should...
It's okay. I have an umbrella.